So the diode circuit diagram looks like that. You notice, the component itself kind of looks like that, something like that. So you guys have all seen this, right? So can anyone explain in like a sentence or two what a diode is? Yeah, or first hand.
It only lets electricity flow in one direction.
Yeah. So by flow you mean, what is the flow? Electrical flow is also known as. You measure it.
Current.
It's the current, right? So yeah. So the basic idea behind a diode is that you only allow current to go one way, and then going the other way, it theoretically it would stop it. So that's like the most ideal. It's so ideal that you can't even call it an ideal diode. It's basically the perfect diode. So the perfect diode would be allowing all current to go one way, stop all current the other way. So what's something that allows all current to go in either direction? Like what do you guys use just to pass current through things? Yeah. Just wires, right? So in the forward direction, it looks just like a short circuit, right? Just like straight up. So if this was two terminals, it would look up like that. So what would the reverse look like in the perfect condition? What else would it look like? If you could model one way as a short circuit, what would you model negative current as? What's the opposite of a short circuit? A what? Get out of here. What? So the short circuit, it'll allow huge amounts of current to go through. What allows absolutely nothing? Absolutely nothing. This thing actually can't even really technically exist in the real world. What's the perfect insulator? How would you represent that in a circuit diagram? Yeah, a disconnect, an open circuit. So, as in like, just like that. Nothing between it, just nothing. So there's absolutely no way to go between it. I mean, like, of course, like, realistically, there's always going to be, like, a tiny, tiny bit of resistance, and there's always, like, eventually you'll get current to go through, even in air. But, so, yeah, we're thinking of, like, perfect situations here, right? Because the idea behind all these things are called abstractions, which is when you kind of just, like, tell yourself that these things that exist don't exist just to make your life easier, to make it actually possible to do things. So, for all intents and purposes, the diode, when one direction looks like a short circuit, the other direction looks like an open circuit. So this is what we do, like even professional engineers, when they look at a circuit and they're trying to figure out what's going on, they don't do all these mathematical equations and run through all these, they don't actually go through the math and the graphs and things of what's going on immediately in their head. So for you to figure out exactly what's going on, you start to think of it like this. So you look at the circuit that has all these diodes everywhere, right? So you start thinking to yourself, okay, let me imagine current going one way. Now let me just replace all these diodes with just shorts. And like, let me think of it the other way. Oh, let's replace them with all just opens, right? That's like a good way to think of it. Or like, not a good way to think of it, but like a quick way to think of it, so you can actually see, you can kind of get an idea of what's going on in your circuit. So, let's see here. So that's like what's perfect, what you want it to be. So if you were to graph that, if this is current versus voltage, so that's adding a voltage difference here, and the current I is how much current is going through the diode. So what would it look like before zero in the negative voltage range? So where would the current be? Would it be opposite the normal way? Would it be negative current? You're saying it would kind of go down like this? You're saying it's somewhere in this line?
Yeah.
In negative current line?
Yeah.
So that's what she says. Anyone else have a different idea? Zero. So we have two ideas. So we have negative voltage land or just straight zero. So who thinks it's negative voltage land? Not even you? You changed your mind? Okay. So who thinks it's zero? Yeah, so majority wins here. It's actually just zero. So, I mean, that's the point, right? Is that in the reverse direction, you get no current because it gets blocked. So it would just be zero. So everything before zero in voltage is zero in current because nothing happens, nothing goes through. So now what happens so this is the perfect situation. What happens, what would it look like once you get to positive voltages? Yeah, so the thing is, like, of course, so ideally you're not limited by a certain amount of current, so ideally you could pass however much, so if the voltage could go infinitely high, then your current would also go infinitely high accordingly. And if you had like a small enough, because V equals IR, so it would end up looking like this, like a straight line up, right? Which means that at any voltage, depending on the resistance, you could have an arbitrarily high amount of current. So that's the graph of what is like the perfect ideal diode, like the model of the diode looking like a one-way valve. Because if you can think about it, the diode, I mean, you guys get it, so you don't really need too many analogies for how the diode works. But it's basically like a water valve like this, like a one-way valve. So water can go out this way, right? But if you try to get water this way, it'll get blocked, yeah? So that, if you model it on an IV curve, looks like that, right? But of course, it's physics, so of course physics is never ideal and never perfect, so that's not actually what's going on at all. So we'll go into a little bit of exactly how diodes are made. So you guys have been seeing these things going on, and you've been like, you know how they work kind of, and you've been using them effectively. And you get, so what's the most important thing about the diode that you guys have learned from your experience using them? Or what's the most important thing about them? Yeah.
They're polar.
Yeah, which means
They have to go one direction.
yeah, the direction, right? So you got to make sure that you put them in the right direction. That's what's the most important thing about it, right? So that's like the biggest mistake you guys are making is that you're putting them in the wrong direction. Probably the only mistake you guys can notice for now is that you're putting them in the wrong direction. So what that means is, you know, obviously it's blocking it. It can't go the other way. So you're getting, you know, here a negative current land, it's getting blocked, right? But to understand what's actually going on inside of it, does anyone know exactly, or at least have an idea of how a diode works, how it actually achieves this fact of being one way? Okay, yeah. So it's a little bit, it has to do with, has anyone ever learned about like p-n junctions or like semiconductors? Okay, we'll go into a little bit of this. So this is like a huge area of study that you can spend like years and years and years studying. And you'll most definitely get to it in college when you do like E&M physics. Or if like, I mean, hopefully some of you guys will go on to be electrical engineers. You'll definitely do it if you're an electrical engineer. But it has to do with silicon. You guys have heard of silicon, right? I mean, Silicon Valley, right? So do you know why they call it that? Yeah.
Because I'm computer chips made of silicon.
Yeah, that's like the basic. So the point is that like metals conduct, like something that's an insulator wouldn't. But then you get these semiconductors that conduct in like very specific cases, which becomes useful because then you can use the specific case of the conductor. So here, this would be an example of a semiconductor. So it's eventually germanium or silicon or something in there. And if you look at the energy levels, you guys have all taken chemistry, right? And physics. Or chemistry now? Okay. So most of you take chemistry, right? So you learned about energy levels? Energy levels? Right. So you guys know about like everything kind of, so if you can imagine all the little electrons in here, they all kind of have like energy levels. So all these guys have like energy levels associated with them, right? So a higher energy levels are kind of like potential energy. So what does that sound like to you guys? When I say potential energy, you think what? Yeah, when I think so when I say in the terms of electrical, in terms of V equals IR, when I say potential energy, you say V, I, or R. You got a one and two chance.
I.
What? All right, so who says I? Who says I? Who says R? And who says V? All right, nice. All right, you guys fixed yourselves, right? Yeah, so when I say potential, you say voltage, right? Because that's what voltage is. Tension, potential, voltage. That's basically what's going on. So you can look at the potential of these electrons right before the diode as the, you know, as the potential energy. So if you think about it, it's kind of like a cliff. Right? So electrons coming from this end, they can go one way because all they have to do is fall off the cliff. That's easy, right? You can fall off the cliff at any arbitrary speed. Pretend it's a perfect vacuum, so there's no air resistance or any of that. So they can fall off the cliff, right? And then this is the, right there. So you can fall off the cliff easy, but coming back this way, you can't get back up the cliff, right? But I mean, of course you can get back up the cliff if you have like even a high enough ridiculous amount of voltage. So that's like the, you know, eventually when you, on the reverse current, it'll break down at like 75 volts. So let's say it takes like 75 volts to get across this big huge, to get across this big cliff. So it takes 75 volts and going this way theoretically would take none, because theoretically it works perfectly just like this. So that's the ideal case. That's kind of what you can think of going out the energy levels. But now we're going to go into what's actually happening. So what actually happens is that instead of being a perfect cliff that falls off like that, it looks more like this. So can anyone, if the other case would look like this, can someone tell me what this would look like on this graph? All right, that's fine. We'll go through and see exactly what's going on. So let's try to explain it. So these are all electrons that all need a certain amount of voltage to, well, they needed a certain amount of voltage to fall down, right? To fall down, you don't need anything because you just fall. To go back up, you need a huge amount to go up. Now, what do they have to do now before they can get to the other side? Go up just a little bit, right? So what does that mean? Yeah, it needs some, yeah, perfect. It needs some amount of voltage. We call that VTO for V turn on. So it needs some amount of little, even just a little bit, just to get over the hump, just to get this thing working. So if you think about it, it's not a perfect valve. So it's not like, it doesn't work like everything in one direction goes, everything in the other direction doesn't. It's kind of like, now we've gone and we've progressed to, in the reverse direction doesn't ever go. In this direction, it can, but as long as you pass VTO, because you need to give it at least enough voltage to make the thing work. Because if you don't give it enough voltage to make the thing work, it can't even get over the little starter hump. So that's what happens in like this area, like low voltage land. So you might notice that like if you use an LED, which is an LED is a diode that emits the energy as light. If you have like really low voltages, like 0.5 volts or something, it's just not on at all. It's just completely off. And then as soon as you get to like 1-ish volts, suddenly it just starts turning on. It'll go up exponentially. So now you've got a better model of what's going on. And of course, like everything has a little bit of resistance, so this is going to have a little bit of resistance. It's going to use a little bit of energy. So we kind of draw it like a curve like this, because it can't be perfect, because it's not going to pass an infinite amount of current, depending on the resistance, because of course it's going to have resistance associated with it. So now we've got a model that looks like this, where you need to at least get to VTO, then it'll start turning on. And it's not going to turn on perfectly, because this thing has some resistance associated with it. So that's the next step of what's going on. So now to get the final step of exactly what's going on. The thing is that all electrons aren't the same, and they're not all at the same energy level. So you guys know this, like some electrons are at higher energy levels than others. Some are going to be able to jump over this hump before you even give it enough voltage. So as soon as you go to positive voltage land, there's going to be a few electrons that have enough energy to get over this hump. So, and then as you go up, there'll be more, until the majority of them start being able to go up, and that's V turn on. But before you get there, when you're still in low voltage lands, you're going to get tiny amounts that are able to, so kind of like that. Kind of a bad drawing right there. So trying to exemplify, it's really a small amount until you get here. So if you can kind of see there, right before you get to V turn on, there's still a little bit that can go. So you can get a little bit of current, but you're never really going to notice it. And that's the IV curve of the diode. So the IV curve is in like, I mean, I've had like several classes dedicated entirely to the IV curve. Like you can really get into this. And a lot of people really get into that. That's basically like the foundation of a lot of like semiconductor physics. It's very important to know. So you guys can understand that's what's going on with the diode. Anybody not get that? How we went from the perfect case of the straight up and down side to what's actually going on is like that. So what this means is, okay, so let's go through like some cases of you troubleshooting your circuit. So you've got a circuit, right, with an LED, and let's say you hooked it up and you turn the thing on and it doesn't turn on. So what could happen? What could be wrong?
Voltage isn't high.
Yeah. So you could be living in low voltage land, right, where it's not turned on yet. What else could be wrong? Yeah, you could be in negative voltage land. Both those cases, you have not enough current. Perfect, yeah. So those are the two things you should look for when you've got something that uses diodes that doesn't work. So you got to make sure you're not make sure that you're in this good, high voltage land past VTO where things are working exactly like you want them to be. Cool. So that's how a diode works. Actually. So let's see here. Does anyone know what an LED is? Or I mean, you guys all know what an LED is, right? Light emitting diode. So does anyone know how it emits light through the purpose of this diode?
Can I guess?
Yeah, you can guess this
Like
one.
dissipating energy in the form of light?
Yes, perfect. So how did it dissipate energy before? When you've got a usual diode, how does it dissipate most of its energy? Heat, right? Yeah. So you might notice that your diodes get really hot if you're running a lot of. That's why if you have like a power diode, I don't know if any of you are using power diodes, but they've got to be really big and chunky because they've got to take in all that heat because it dissipates a lot of energy. So that's, with this energy diagram like this, when they go down the slope, it's like if you fall down a cliff, right? Like that's a lot of energy. That's a lot of stuff going on. That's a lot of turning potential energy into kinetic energy. So when you hit the ground, that's like a huge splat, right? So that's a lot of energy. So usually that was dissipated in the form of heat, but here now we've got that dissipated in the form of photons. So you guys know what photons are, right? What is a photon? Yeah, ish. So, I mean, it's fine. You can think of it like that. So, you've got these electrons. They got excited enough to get over this first hump. Now, when one electron is falling down here and it's using all this energy, each one electron emits a photon. So for each electron that's falling down this thing and losing all this energy, passing over this diode, you've got all that energy, a photon for each one, and then if you've got like luminescent materials like, I can't remember the names, I think it's like gallium arsenide or something like that, then it's dissipated in the form of light. So then you've got each one dissipating light, and that's how you form an LED. Circuit diagram is either two arrows like this, or sometimes you'll see I'm not very good at the lightning bolt. I could never draw lightning bolts, so they confuse me. So you got these little two lights. That means that the energy is being dissipated as light, so you can see it. So with a diode, right, you've got V and I, right? You've got your voltage and your current. So can anyone tell me what the current means as far as an LED? Like what can you experience the current as with your like senses? How could you know? If I were to give you two LEDs with different currents, yeah.
Can you see light coming out?
Yeah, exactly. But like that's just if they're getting any sort of current. If they're getting any sort of current, they're going to be on, right? But how can you tell the difference between an LED that's getting low current and an LED that's getting high current? Yes. Brightness, right? So, yeah. So more current going through means more energy being dissipated off, right? So do you remember from earlier the vehicles IR lecture about what was current? Like if these are all little electrons, what's the current through like here? In terms of what? Yeah, exactly. But I mean, like, what does it mean in terms of these electrons, all the little electrons? You can imagine them as the little cars on the street. So remember, you're looking at one intersection on the street, and the current is. Anybody remember what the current was? Remember it's how many.
Oh, electrons.
What?
Isn't it like
How many electrons?
So it pass.
Yeah, right. So if you're going to count how many electrons go down this slope, that's the current, right? So remember, each electron is one photon. So higher current means more photons, exactly, which means higher brightness, right? So this is when it's all coming together. Now current. So hopefully that'll give you like a nice visualization as to what current means, and what it means in the circuit, what it means physically. So this is what I mean by like V equals IR. Like when you first learn about it, it doesn't really make any sense, and like we don't expect you to make sense of it. But with little applications like this, you're like, oh, okay, I can see what current means in that case. So now we're gonna get a little bit weirder, and this will be, you guys might not get this one, but so if current is the brightness, which means more electrons going down the slope, which means more photons being emitted, which means more brightness. What does the voltage mean? As in, like, what's the difference between this slope and this slope, and let's say this slope? Because this means higher voltage, right? Because now this one's got much higher VTO, And this has got, let's start with the graph first. So I've got A, B, C. So what are A, B, and C going to look like in negative voltage land? Just straight up 0, right? So where's VTOA going to be? Yeah.
Is it going to be like a little higher than what it would be because since the slope is lower, more electrons can get past it.
Yeah. So does that mean the voltage? Does that mean VTO is going to be higher or lower? Lower, right? So you're going to have, let's call this VA, VB, VC. So VA is going to kind of look like that. VB is going to kind of look like that. C is going to kind of look like that, right? So you get three different ones. And at three different voltages, they're all going to go on. So at the little voltage, A is going to be able to shoot out. A little higher, B is going to shoot out. A little higher, C is going to shoot out. All right, so back to what does that mean as far as what you see? So what does the voltage mean as far as what you see, yeah?
Well, it means if you have a higher voltage, it's like going to turn on.
Yes, but how could you know? So if I was to give you 3 LEDs that have already turned on, exactly. So these 3 LEDs are already far past. That's the voltage is way up here. They've
How
already
often
gone.
they flicker?
Not quite, but kind of like that, a little bit. Think about it. So that's how often they flicker, right? How do you measure flickering?
Maybe per second.
In what? Right. So would that be like, so how many times per second? Which is like hertz, yeah? Right, hertz? Okay. Honestly, it's kind of ish on the right track, yeah?
Would it mean that each photon then has more energy, so the,
Kind of, yeah.
would the frequency of light be different?
Yes.
So a higher frequency for you see and
Well, no, I don't know about frequency of light, but ish, like light. What's 1 over frequency?
wavelength.
Yeah, so opposite wavelength. So shorter and long. So it varies the wavelength. What does varying the wavelength do?
Changes the energy.
Change the what? Is it?
Color.
Yeah, the color, right? Yeah.
Oh.
So these are 3 different colors. Yeah, there you go. That's actually cool that you guys were able to work that out. So you're looking at 3 LEDs here. All these 3 LEDs would have different colors. So does anyone have a guess as to what the first one that would turn on would be?
Right.
Yes. So I mean, okay, within the scope of red, green, and blue. So because really it would be like IR, right? So you got red turns on first because
Because it has the longest wavelength and the least amount of energy.
yeah, exactly. So it takes the least amount of energy. That'll be an easy little thing for that. So in order to get those long wavelengths, it doesn't take much voltage to send those photons on their way. The next one that would turn on would be what? Green, yeah. And then blue, right? So if you're looking at 3 different graphs and you have to match these to 3 different LEDs, you would look at their color for the voltage, and you would look at their brightness for the current. And that's basically what's going on with LEDs and diodes. So when you guys are looking through your circuit, so you guys know, like, if something's wrong with it, most likely, like 9 times out of 10, you flipped it around. Something else that could be wrong, you haven't reached VTO. So like, let's say, so with those 3 diodes, so let's say you've got like red, green, and blue LEDs, and your red's on and your green's on, and your blue's not on, and you've turned it on. So what could be wrong? What? Yeah, because you could be living right here in a land where red and green have turned on, but blue hasn't turned on yet. Or blue could just be put on backwards. You gotta check it out. So that's what's going on with diodes. If you guys go on with physics, especially electrical or E&M, or like device physics, if you do electrical engineering in college, you'll see a lot more of that. I guarantee you'll see a lot more of that. So that'll be a good introduction.